Find the magnetic field due to a semicircular loop of radius A carrying current I. We have the formula for magnetic field due to a circular loop carrying current. B is equal to mu 0 Ni A square by 2 into A square plus X square raised to 3 by 2, where A is the radius of the loop, X distance from the center of the loop. Case 1, for a point on the center of the loop, X is equal to 0. Now the equation becomes mu 0 Ni by 2 into A square. Here distance X we can put 0. So here X is equal to 0. So now we have 2A square raised to 3 by 2 or 2A cube. On cancelling we get B equal to mu 0 Ni by 2A. So this is the equation for magnetic field at the center of a circular loop. In the case of a semicircular loop, we have only half the turn, so n is equal to n by 2. So for n, we can substitute n by 2. In substituting n by 2, we get mu 0 Ni by 4a. This is the equation for a semicircle. Next, if we consider 1 by 4th of a circle, for n we can substitute n by 4. So in the equation we substitute n by 4 instead of n. Now the answer becomes B is equal to mu 0 Ni by 8a. Here our question is, find the magnetic field due to a semicircular loop of radius A carrying current I. That is the second case, B is equal to mu 0 Ni by 4a. Our next question is, a wire loop formed by joining two semicircular wires of radius R1 and R2 carries a current I as shown in figure. Find the magnetic field induction at point O. So here we have two semicircular loops. Instead of one, we have two semicircular loops. One of radius R1, other of radius R2. Both carries current I. We have to find magnetic field at center O. Now we can use this equation. That is the second case for a semicircle. N is equal to n by 2 in this equation. On substituting n by 2, B is equal to mu 0 Ni by 4a. So this is the equation for magnetic field due to a semicircle. B is equal to mu 0 Ni by 4a. We are going to use that equation. So magnetic field due to semicircular wire of radius R1, instead of A we can write R1. We can call the magnetic field B1. B1 is equal to mu 0 Ni by 4 R1. And magnetic field due to semicircular wire of radius R2, we can call it B2. The equation is mu 0 Ni by 4 R2. Instead of A, we can write R2. Both carries current in the same direction. So magnetic field due to both are downwards. The same direction, that is into the coil. So the net magnetic field B is equal to B1 plus B2. So we can add this 2 from equation 1 and 2. Mu 0 Ni by 4 is common. So net magnetic field B is equal to mu 0 Ni by 4 into 1 by R1 plus 1 by R2.